Hey folks! So today I'm going to give you a little run through this data structure called a graph. So we're going to be thinking about graphs. Another name for these guys is networks. You may have seen these before, but yeah, figure we better introduce them here. So starting off with a simple undirected graph, has two parts to it, the vertices and the edges. The vertices, alternatively you'll hear me call them nodes. I'll slip between those kind of without noticing, but yeah, nodes, vertices, same thing. And the other part is E, the edges. And for an undirected graph, these are two element subsets of the vertices. So there's your vertices. Let's just use the letters A, B, C, D, and E. There's your edges. So your edges are two elements from V together in a set. So this is some reminders about set stuff. In sets, remember, order doesn't matter, right? Sets as a data structure don't care about order. That's why this is going to be undirected. Let me go ahead and try and draw what this represents then. So we have A, we have B, we have C, we have D and E, say like this. So let's see, what connections do we have? Well, A and C are connected, so I'll draw a connection between them, right? They have an edge. B and C are connected, so I'll draw an edge there. E and A are connected, so I'll draw an edge there. D and E are connected. D and E are connected, and E and C are connected. All right, so that's the 1, 2, 3, 4, 5 connections drawn in. And so you can see a graph, it's kind of like a tree, except now you can have these loops, right? There's no longer like this hierarchical structure where you can walk down the tree. Now graphs can have like loop shapes like this. Let's check out another kind of graph. Give you some more ideas about this. Another kind, directed graphs. These consist of, again, vertices. But now the edges are going to be pairs of elements from V, aka the set of edges is the subset of the Cartesian product of the vertices with itself. If you're not sure about that notation, don't worry about it. Just, figure I'd throw it in there for folks who know their CS 2233 materials, their discrete math materials. So vertices, same set. Edges, now instead of having curly braces, I have parentheses. So like A, comma, C, this pair is not the same as this pair. There's a directedness, like from this guy to this guy. So from D to E, for example. Let me draw in the same vertices here, like that. So we can go from A to C. So I'm going to put an arrow to indicate the direction we can go. A to C. We can go B to C. All right. We can go E to A. All right. We can go D to E. D to E. Yeah. E to C. Okay, so E can go to C. But then actually there's one more edge, C to E. So actually this guy, E to C, C to E, this is kind of the same as our original undirected edge. Now we have two directed edges to get the same effect. We can go either direction. In terms of thinking about these guys, there's a lot of related problems, and we're going to look at some in short order. But I often think of it as a starting point, like bus stops. Like these are locations where buses can stop, and then the kind of connections you have are maybe routes. Like there's a route going from D to E, so you can go from this bus stop to this one, or E to A. But there's not a direct route from A to E. If you want to go from A to E, you gotta go to C and then to E, right? You have to take sort of an indirect route there. Okay. So that might give you some ideas of what these are going to be useful for, right? They no longer have that hierarchical tree structure, but they've gained something, right, in terms of representing connections. Just a quick side note here before we get on the next page. How many edges can you have? Well, it turns out the most edges you can have can be quickly upper bounded as the number of vertices squared. Why? Well, because we're not going to allow duplicate edges. So stuff like this is not allowed. You can't have two of the exact same edge connecting two things, right? See, E to C and C to E are different. Here it's just, let's say this is X and Y. These are two connections. They're exactly the same. Not allowed. Okay, so just thinking about the number of possible connections, well, it's going to be the number of vertices. Let's say the number of vertices is how you rate number of vertices is n. That's going to be n times, well, it seems like it'd be n minus 1. You can actually have n squared different connections. It turns out you're also allowed to have connections from a vertex to itself. In our bus route example, I'm not quite sure what that means, to take a bus from a node back to itself. But yeah, there's n squared possibilities, right? N things you can put in the first position, n you can put for the second. That's an upper bound on both of these. Undirected graphs have a little bit of a lower upper bound, but before we get to trying to bound these two exactly, let's go ahead and think about some applications for this. Okay. So these pages have a bunch of color on them, so I didn't want to print them. But these are just the next pages in the notes. So why graphs? Why are we interested in these things? Well, they're useful in a bunch of situations, but to put it as generally as I can, if you got a bunch of things and you're interested in the relationships between pairs of those things, graphs might be what you want. There's a good chance the graphs are relevant. Some example graphs like Facebook or whatever your favorite social media platform is, the follows and friends on that social media platform are actually a kind of graph. You know, A links to B, B links to C, that kind of stuff, right? Also, like another one you have seen in sort of regular use is any of the like street map websites, right? Like Google Maps, for example. You have to be able to represent a what connections are available for you to drive along, right? If you want to have a map tool, and a good way to represent those connections, well, could be like with a graph. Then you can figure out, okay, is how would I get from city A to city B, right? What's the route? And that gets into applications. Like things we can do with these, well, there's navigation. Like figuring out, well, not just is there a route from city A to city B? There probably is. What's the best route, right? What's the best route to take? You know, if you're driving a car, or if you're taking a bus, or if you're flying by plane, you know, what's the best route? Other applications, well, it's used actually in AI, it turns out, neural networks, 3D graphics. Yeah, if you know a bit about like 3D models, those are a kind of generalization of graphs. Games, constantly used in games, especially games where you need to do routing sorts of stuff. These things called flow networks. I'll give you some intuition about that in a moment. Finite state machines, might also know these as Mealy or Moore machines, if you come from a computer engineering background. And yeah, lots more stuff, right? This is just the tip of the iceberg. So applications, I got a whole bunch here with links to more details if you're interested for some of these in digging more deeply. The first one actually comes from my doctoral advisor, something she's been working on, which is taking a map of a city. So this is a map here, which is being represented actually by a graph. You can think of anywhere we have sort of an intersection. That's maybe a node or vertex in our graph. So this is a city map of, I believe it's Chicago. Yeah, Chicago Road Network. And then there's another kind of graph thing going on top of that. You see all these gray lines? Let me zoom in real detailed so you can see it. See all these like gray lines zigzagging back and forth? These are actually GPS trajectories that they've recorded and are trying to use to reconstruct the road network from. So by using sort of the GPS navigation in cars, they're trying to reconstruct a road system from that to make sort of predictions of what the road network looks like. So here you can see those sort of overlaid, and they also have reconstructions on their websites using that. Okay, let me zoom back out. Okay, so that's one application right there, right? Representing like a road network of a city, representing trajectories, like this weird like bunch of trajectories, these GPS trajectories. You can see they wiggle off the road because there's like an error associated with the GPS trajectory, especially if you're around tall buildings. The positioning can actually be off. There's another one I want to associate with this graph, which is that flow network thing I mentioned. You can think about cars flowing through this system. Say cars starting on the, if we're in San Antonio, maybe starting like outside of Loop 1604 and flowing downtown. And you could think about how the cars will travel to reach downtown, starting from like outside Loop 1604. And you could actually try and detect locations in your road network where there'll be bottlenecks. Yeah, where your cars will, fully utilize a road, right? That would be stuff with flow networks. That also can be used for a bunch of other stuff. You can use it for like literal plumbing, but you could also use it for like circuits. So yeah, flow networks, really cool thing. Here you could think about this as like a flow network, trying to figure out how cars flow through your graph. Okay, so yeah, that's an obvious one. Just to throw another one on this, here's an image. It's actually from an animation, but it's not easy to put animations in my slides, so I just took the last image from it. This is from a game called Factorio, a real cute game. But you have in this picture like a bunch of nodes you can see, and then sort of links coming out from them. This is an exploration on a graph. In particular, there's a bunch of little like cute bug critters in this game that like to attack your buildings that you're trying to construct. And they're in this picture, I think, in the top left corner, and then they're trying to navigate to the bottom right here. Where my mouse is? Yeah. So the ideal path for them would be to follow this like red straight line between those points, but there's water in the way. So they have to sort of hike around the outside to try and get to their target location. And so this is actually a route finding algorithm that they implemented, called A-star, but very well known. And so they saw a whole bunch of improvements on their routing by doing some clever tricks, which was kind of cool. So maybe that's an article. If you're interested in that kind of stuff, if you're interested in video games, you might find that one more engaging. Check it out. Some more applications here. Let's throw up some more. Here's a mesh of a dolphin. It's like a 3D model, and you can see, you can picture this as a graph, right? It's made of triangles. This is called a tessellation, when things are made of like these little triangles. But this guy is actually, you could also think of it as almost a more general structure than a graph, because you're actually representing like a surface. Yeah, so you're taking triples of points, taking instead of pairs of points, you're taking triples of points. Nonetheless, yeah, some graph stuff that applies in these sort of computer graphics applications. Another application I mentioned already, but like social networks. If you have a social network, you can have a bunch of different like entities in that, and they can have a bunch of different relationships, right? You can have this person who watches YouTube, right? So they interact with YouTube. They like, this particular photo. They're a friend to this particular person, right? And maybe they follow, right, or listen to this, this Last FM. So, they could have like all these connections, and you might even want to model what kind of connection they have, like how they're engaging with that content. In that case, you could represent this as a kind of graph where the connections have labels. Turns out that's a good idea, labeling your connections. And I have another social network sort of graph here. This is, it's called a sociogram in, I guess, the sociological applications it's from. But it's 8th grade students' seating preferences. So the nodes each represent students. The arrows represent who they want to sit next to. Some of them seem to have no preferences, but yeah, I think every node can have at most 2 preferences, like a left and right neighbor. So everyone's trying to pick who they want their left and right neighbor to be. So you can see some people are very popular neighbors, and some people are less, popular neighbors. And so they were looking at this to kind of look at social dynamics, right? So they're a nice way to draw, a visualization for that social dynamic is a graph. Okay. And I got one last application for you down here, just rapid fire. Which is one I actually found really interesting personally, which was AlphaGo, this Go playing program that the Google DeepMind people came out with a few years back. So really, it was this really strong Go playing program that beat effectively like the best players in the world. It was sort of a surprising result, because a lot of people still thought Go was going to be this very hard problem to solve. It uses, of course, AI, and in particular, the kind of AI stuff it's doing involves this thing called a neural network, and a neural network is a kind of graph. So this particular image actually isn't from Google. I went and grabbed this because I liked that it had the pictures of the Go boards, as well as showing kind of what a neural network looks like. I can't vouch for the accurateness exactly of this, but I do have a link to the article where I grabbed it from, and so you can check it out if you're interested. You can also check out Google's put together a ton of stuff about it if you're interested in that. But yeah, so if you know anything about Go, or if you're interested in AI, this is a really cool application. And you can see, the graphs basically are kind of all possible connections. It's actually sort of flowing left to right. And what you're trying to do is make a decision given a particular board, right? You want the algorithm to be able to make a decision based on a given board state, like this input, to say where it wants to play. Yeah. Okay, so not going to go into all the details for all those applications, obviously, because, we'd be here all day. But if any of those struck your fancy, go follow the links, dig up some more details if that sounds like a fun time. But otherwise, I'm going to jump back to the notes. Okay. So coming back to the DocCam here, and over to the next page. Let's think about bounds on the number of edges. I said we were going to come back to this guy, right, and be more specific in our bounds. I already showed you that the bound on a directed graph is the number of vertices squared, right? Because it's going to be your first position in the pair. You can choose from the number of vertices. Again, this is number of vertices. This is called cardinality. It's taking the cardinality of the set, right? So you can choose any of the vertices for the first position, and you can choose any of the vertices for the second position. So the number of combinations kind of within there is number of vertices squared. Okay. But what about an undirected graph? Is this guy significantly less? Because now with an undirected graph, I can't have connections of this form, right? I can't have any connection, any duplicated connections, and that means you'll never have two connections between a pair of nodes. Also, it turns out in an undirected graph, you can't have self loops. So you can't have a loop from A back to A. The reasoning here is a little bit tricky depending on your acquaintance with mathematics. But the idea is you can't have two elements that are the same inside a set. A set only tracks like what's in it or not in it. So a set that contains two copies of the same element really is just the same as a set that contains one copy. There's no distinction. So that's not allowed either. Let me cross that off. But does that change our runtime, or excuse me, getting ahead of myself. Does that change our bound, which will affect our runtimes later? Not really. The logic here is you're going to instead be choosing two elements. So this is going to be choose 2 from V, right? So choose 2 from V. Turns out the number of ways you can do that is represented by this guy. This is not a division, right? It's not this. It's this choose function, which is equal to this, which is equal to this. And in particular, this should make sense because this is the number of pairs you can have, which excludes duplicates, right? So we're excluding the duplicate. And then you're going to have half as many as that because edges like AB, this is the same as BA, right? So everything can be written two different ways, so we cut it in half. Of course, effectively, both of these are still, they go number of vertices squared, right? This one is roughly half as many. So whether you choose directed or undirected doesn't make an asymptotic difference to the number of edges you have. Okay? And just to show that off for fun, that this formula is right, again, if you're not 100% sure on the math, I can hopefully convince you at least for 4 vertices. Let's draw as many edges as we can for 4 vertices. Let me give them names, A, B, C, and D. Let's say, well, A could be connected to all of these. Then B, well, B's already connected to A. I connected to C and D. Then C, well, it's connected to A and B. I can connect it to D. And D, it's already connected to everybody, so there's no edges possible to add. So if we look at this, this is 1, 2, 3, 4, 5, 6, right? It's 6 edges, 4 vertices. And if we go up here and look at our formula, the formula tells us it should be 4 times 4 minus 1 over 2. Right? That's just plugging into this formula, which gives you 4 times 3 over 2, which is 12 over 2, which is 6. So indeed, this bound is sharp. This is like a exact upper bound. You actually can have that many vertices. Okay, so Oh yeah, one more thing I was going to mention. Complete. That's what I wanted to mention here. Complete graphs are graphs which have every possible edge, right? So this is kind of every possible edge. You could also think about making the complete directed graph of 4 vertices, and you could check the number of connections in that one. It should be, if this is right, 16. So check that out. make sure that is true. But yeah, that's what I wanted to say about bounds on the number of edges. Another thing that's going to be useful for us in analyzing all these nice graph algorithms we're going to look at is the degree of the vertices. So the degree of a vertex is the number of things that are adjacent to it. We use this term occasionally for trees as well. But yeah, we're using it for vertices in our graph. So let's go ahead and just label these guys with their degree. Let me see. For the one on the left here, this has 2 edges that it's involved in. B has 4. C has 2. D has 1, 2, 3, 4. Right. E 1, 2, 3, 4, 5 connections that's involved in. I has 3. H has 3. G has 3. And F looks like it has 4. Okay. So, and the way you can write this, I'm not going to write it in for all of them, is degree of, right? So degree of A, for example, equals 2. All right? And it turns out there's another thing called in degree, out degree. These don't make sense for a undirected graph, but for a directed graph, in addition to thinking about just regular degree, which in this case they would be the same numbers, right? It'd be the same numbers if we're thinking about degree. We could also think about in degree and out degree, which are the number of incoming edges, drawn with a minus sign here, number of incoming edges, and number of outgoing edges, drawn with a plus. The way I usually think about it, to keep it straight in my mind, is outgoing edges are plus, because those are the ones that are actually going to be important for a lot of our algorithms in determining cost. So these guys are adding cost to exploring the graph. Incoming, they don't directly add to the cost of exploring that current vertex. But yeah, however you need to remember it. Let me do all the incoming first. A's in is really easy. It's 0. Right? There's nothing incoming into A. That's fine. B has 2. C has 2. E has 2, where I'm just counting the arrowheads kind of going into them. 2 for D. I is just 1. H is 2. G is 2. F is 2. Okay? Let me choose a different color. Let's do outgoing edges. So let's see. Outgoing edges, A is 2. B is 2, C 0, that's possible, D 2, E looks like 3, F looks like 2 outgoing, I 2 outgoing, H just 1 outgoing, and G 1 outgoing. Okay, so there's your kind of in and out for every vertex. Okay, so hopefully you're all right with this. I don't think there's too much to degree. I think they're straightforward. There is kind of a cool trick with degree. This will come into play with some of the analysis. It's a nice trick for analyzing some of the runtimes. This is called the Handshaking Lemma. So the Handshaking Lemma observes that, hey, if you sum up the degrees for every vertex, so this means sum for each vertex, right? That's that summation. Sum for each vertex V, its degree, you get 2 times the number of edges. Really? Okay, let's check that. Counting up here, 2, 6, 8, 12, 17, 20, 24, 30. 30 is our total. Total degree equals 30. And if we cut that in half, 30 divided by 2, that's 15. And yeah, the number of edges is 15. What the heck? The degree sums out to be double the number of edges? How do we know that? Well, I have the hint right there, I guess. Every edge is counted twice. right? You count the edge once on the sort of left side, or however you want to think of it. We count it once on this side, and we count it once on this side. So every edge gets counted twice. Yeah? So this guy creates 2 degree. And so if you count up the degree, you overcount the edges by a factor 2. This is compared to the name, comes from handshakes. If you're at like a party and everyone's sort of shaking hands, like you have a bunch of people meeting and shaking hands, and then you asked everybody how many hands they shook, and then you counted that up, that would be 2 times the number of handshakes, right? Because every handshake has 2 hands. I don't know if that's any more helpful than just this observation, but if you're curious, that's why it's a handshaking lemma. Okay, moving on. Directed graphs, also really handy. No pun intended. You can see that actually the in degree and the out degree also have to sum up to exactly the number of edges. And let me just check that real quick. Let's see, doing it for, well, we'll do it for the out degree first because I grabbed the blue pen. So let's see, it's 2, 4, 6, 9, 11, 12, 13, 14, 15. Yeah, okay, it summed up to 15. Let me count the other one. Let's see, 0, 2, 4, 6, 8, 10, 11, 12, 13, 14, 15. Oh, okay, they both sum up to the number of edges. How did I know that? Well, of course, every edge is directed. So every edge adds 1 to the out and adds 1 to the in, right? So every edge adds 1 to each. And so if you count these 2 guys up, they're each just going to be the number of edges. Okay, so these will be useful for some analysis stuff, but figure I'd toss that in with the counting stuff. I think we're about ready, though, to do some more fun things with our graphs. Thinking about representing graphs. So far, I've been representing them by just giving you pairs, right? I've been doing things like, hey, A paired with B, right? Something like that. Or in this case, it's a directed graph, so it'd be A, comma, B. Well, we can definitely represent it that way, but that might not be very efficient for our computer, right? It might not be very efficient if we just have a big pile of connections and then we have to read through all of them. So let me show you 2 ways that we could represent a set of edges inside of a computer. Method 1, this is called the Adjacency Matrix. And this is, I think, pretty clever, pretty straightforward as well. So the idea with the adjacency matrix, just like the name implies, you're going to be given a matrix or 2-dimensional array, 2D array. All right, so we create a 2D array. And the 2D array, its dimensions are the number of vertices by the number of vertices. And the rows represent where you're coming from, and the columns represent where you're going to. And so you can see, I'm just going to put in each of these positions either a 1 or a 0 based on whether I can go directly from this to that, right? So for example, can I go directly from A to B? Yes, I can go from A directly to B. So that's a 1. What other places can I go from A? I could go from A to D, right? A to D. Now, these other positions, I'll draw it in lightly. These are all 0. I can't go directly from A to A. How about A to C? Well, I can get to A to C, but I don't have a direct connection to it, right? There's no edge going directly from A to C. Excuse me, A to C, not A to B. I don't have a direct connection to it. Okay, so let's just fill this in. How about B? What's B got a direct connection to? Well, it's got a direct connection to C. No other direct connections, so all these are zeros. How about C? No connections going out of C. Can't connect to anybody. D connects to B, so it goes to B. Right? Doesn't have to be symmetric, directed, right? So we don't have B to D, we have D to B. Right? No B to D, we have D to B. How about E? Again, no connections in, no connections out. Right? E is zeros in its row and its column. If you live at E, you're going to have a hard time getting on the bus, right? Okay. And so there you go. Actually, we can see we have 4 ones. 1, 2, 3, 4. 4 edges. So 4 ones for the 4 edges. And we have zeros everywhere else. I think that's pretty straightforward as a representation scheme. It's really easy to test for a connection. Testing for a connection just takes like constant time. You just jump to the location and see is it connected or not. 0, 1, time to check connection. Yeah. We call that adjacency. That's the name, right? We check to see if things are connected in constant time because we can just say, oh, is C connected to D? No. We jump to the location in the matrix. It's a 0. The trade-off here is this is kind of expensive, right? This requires the number of vertices squared in terms of storage. We don't usually talk about space all that much, but it is worth considering. If you have a really big graph, like, the graph of all the people who are friends on Facebook, say, that's going to be a big graph, right? It's going to be the number of users times the number of users. That might not be very practical. Moreover, a lot of those people have no idea who the other person is, right? A lot of those are just not going to be interesting connections. Same if it's a map. Most connections, most places are not connected directly on a map, right? So this is not a great representation scheme in a lot of instances. What's an alternative? Well, you could use something like an adjacency list. Okay, so what's an adjacency list? Well, as the name implies, it's a list, instead of a matrix, it's a list of connections associated with each vertex. So for each vertex, we're just going to keep like a list of things that we can reach from it. So for example, for A, we can reach B and D. So we can have B and we can have D. Let's see, B connects to C. C, for its list, well, we don't have anybody. So no connections, right? Nothing. And then D connects to B. And then E, also no connections, right? So how you represent this, you can represent it using arrays, you can represent it using linked lists. Bunch of options here. So these guys, if this is a linked list, this would be a null. This would be a null, right? Like that. Now it's going to be a little bit more expensive to look up a connection. For example, if I have a node which goes kind of everywhere, if this is like a hub, that just connects to everywhere else around it. This person like follows everybody on Facebook. If I want to check if they have a connection to a particular person, right? I'm like, oh, I want to find, is this connection present? Worst case scenario, I have to check all the other connections now. So the cost to sort of check connection and adjacency is now going to be big O of the degree of that vertex. And in particular, it's the outgoing degree. Remember I said out is what adds cost. So the outgoing degree is going to increase our cost to check. Okay, so we've traded away a little bit more time, but of course the benefit is storage. For a sparse graph, that is a graph without a lot of connections, this guy is going to be pretty good because we only need to store space for each of the edges plus the vertices. Okay, edges should make sense, right? We have 4 edges, so I have 4 things in my linked list. Why vertices? Well, even if a vertex has no connections, I still have to represent that by having a null entry in its linked list. So you're still going to need to use space equal to the number of vertices. And then, yeah, if you sum up every node's outgoing degree, you get the number of edges. See, that's your handshake lemma right there. This will be the number of edges because, well, these lists are based on the outgoing degree. Okay. So I think that's all I need to say on those 2 representation schemes. Hopefully you can see, right, there's advantages to each. This one is a little bit faster. This one uses a little bit less memory. As a side note, if it's the case that this guy has a very dense graph, so for example, if you have a graph with lots of connections, this becomes the number of vertices squared. So this has a worst case of this. We saw that earlier, right? So you definitely don't want to use these willy-nilly. If your graph is dense, this will behave very badly. If your graph is large but sparse, adjacency matrix will behave very badly. It's your job, right? If you're a software engineer, to choose the right data structure. That includes this. All right. Last little thing here to think about. What about let's just try a very simple algorithm. Try and implement a very simple algorithm. So what's the algorithm? Well, I want to think about finding a path, and let's say we want to find a path that's less than or equal to length k from some starting point A to some ending point B. Right? I want to find some path through the graph. We've already been sort of thinking about that, right? The bus stop example, like thinking about how I would go from, my current location to my target location. That's essentially this problem. I'm asking, hey, is there a way to get from A to B using only K buses? Okay. So looking at the algorithm, it looks maybe more complicated than it is. It's a really simple brute force algorithm. First thing we check, are we already there? Is are A and B the same value? If they are, job's done. There we go. We're already at the location. No need to go anywhere. Otherwise, if our number of connections we are going to follow is 0, well, we're not getting from A to B because we're not there and we don't want to take any buses. It's going to be hard to get to your target location if you don't want to take any buses, right? Okay. Then the for loop here, this goes from c equals 0 to n minus 1. Apparently missing a parenthesis there. So it goes from c equals 0 to n minus 1. These are actually vertices. So we're thinking about vertex 0 through n minus 1 if we have n vertices, for n vertices total. Okay? So we're trying every possible vertex, and we're checking to see, are A and C adjacent? Okay, that's what we just figured out how to do on the previous page. We're going to check, is A adjacent to C? Is there a connection from A to C? Okay, well, we test it with the previous thing, the adjacency list or the adjacency matrix. All right, say they are connected like this. Then, here's the part where we actually try and solve the problem. We recurse. And instead of trying to find a path from A to B, right, trying to find this path, we make C our new A, right? We pass in C, that becomes A, and instead of trying to find a path of length k or less, we instead are now going to be trying to find a path of k minus 1 or less. And that's because we have one more edge over here, right? So we peeled off an edge, so we have one less like bus stop we can go through. Yeah, to stick with the bus analogy. All right, there you go. So this is a recursive solution. This guy will then go and repeat this process. Obviously, if I find a path of k minus length k minus 1 and I have this connection, then I've found a path and I can just return true. I could also return details so I could figure out what the path is. That'd probably be useful, right? You don't want to go onto Google Maps and ask, can I get to Austin from my house in, 2 hours? And it says, yes, you can. So we might, in a real application, want to try and return some more information. But for now, we'll just return true. Yes, you can do this. And then if no C works, right? If you try every C connected to A and none of them work, then no path works to get you to your destination. So we return false, right? Makes sense? Think about it. Meditate on it, as always. Hopefully that makes sense. The question then is this a good algorithm? Is this a good, efficient algorithm that you would like to use? Is this what Google's doing? Take a minute, pause the video, think about it if you need to. So the answer is probably no, right? This is probably not a very good algorithm. It works. That's good, right? I didn't prove it to you that it works. I just sort of hand waved it, but it does. That's good. But the big thing that might tip you off that this isn't great is you have a for loop with recursion in it. That isn't necessarily bad, but it can be bad. Yeah, that can be a high runtime. And so in this case, if we're thinking about the runtime of our algorithm, so our guess is like no, but then we need to justify it. So if we're thinking about the runtime of our algorithm, well, from some location A, how many locations can I explore from it? Well, if there's n other vertices, worst case scenario, I explore all of them, or maybe all of them but B, right? Because if I get to B, I'm done. So I could explore like every vertex, including maybe going back to A itself. That's not a very exciting connection, but could have it. So it's like roughly n connections. And then I have to repeat this. To get to a base case, I have to get to k equal to 0, right? If I don't find what I'm looking for, I have to get to k equal to 0, which is going to mean repeating this k times, right? So we branch out, and then each of these guys could branch out a bunch. So each of these, now it becomes very hard to draw, right? All of these guys branch out. If you want to think about an example, say we have that for clique I drew earlier, right? So say A is in that for clique and B is not in that for clique. If you start exploring from A, there'll be lots of places to go, right? And then there'll be lots of places to go from the places you went to from A. But no matter how you explore, you're never finding a path to B. So you're going to explore every possible path inside of this node, giving you a runtime of, well, basically splitting n recursive calls, and then you're doing n recursive calls every time. So it's like n times n times n times n. Again, it could be n minus 1, but doesn't really affect our runtime significantly. And what this gives us is n to the k recursive calls, and we k before base case. So k recursive calls before we hit a base case, and then each of those could branch each of those levels of recursive calls could branch a factor n. So that gives us n to k. I mean, if k is small, it's not that bad, I guess. If k is 1 or 2, that's feasible. But if k is like 10 or 100 or 1,000, you're going to be in real trouble. So yeah, this is not very efficient, but we can do better. We can do better. And we'll think about how to do better next time. Thank you so much, folks. Hopefully this is helpful. As always, if you have questions, drop by my Discord, ask in class, and we'll continue this next time. Thank you.